Okay. Should we begin? Welcome back, everybody. So we're going to continue with that Bayes factor for model selection. So the problem we're studying looks something like this. So let's say y is equal to x beta, where this right here is a column of the x's, x1, 1, all the way to x1p, x1, n1, all the way to xnp. X, let's just write down, this will be 1j, the jth row, all the way down to xnj. This is the jth row of this. And we can multiply by its corresponding beta. So beta looks like this. Beta 1 down to beta p, and there's this beta j in the middle. So it's kind of a preliminary problem. We're studying this problem. So h naught is beta j equal to 0 versus the alternative. Beta j is something different than 0. So the idea here is if beta j were 0, right here, all of this would reduce to this. Right here, x minus j times beta minus j. So hopefully you can see that. So beta minus j is everything but the j component of this. So beta 1 down to beta j minus 1, beta j plus 1, down to beta p. And to make this all correspond to each other, we have to multiply by something of the correct dimensions when we do it this way. And so this is going to be my x1 vector. So I'm just going to write it like that. So this is just x1 vector. Just to shorthand the notation, all the way to xj plus 1 vector. Xj, this is minus 1. Minus 1, xj plus 1 vector, all the way to, should give myself just a little bit more room. Let me write this just a little bit neater. So x1 vector, all the way to xj minus 1 vector, xj plus 1 vector, all the way to x. So there's p bits of information for every corresponding one. So that's the idea. Hopefully you can see that these are exactly the same. If that were a 0, this reduces to this sort of thing where we've just kind of ripped out the j column. So they're equivalent to each other. That'll be important in a moment to understand that correspondence. But this isn't our goal specifically, just figuring out if the j variable coefficient in there is a 0. We have a loftier goal. And so let's remind ourselves what that goal is. Help me. So, and remind me what the overarching goal is here. What would we like to do? Right, so you wanna find your best model in some sense. But a Bayesian, anytime there's uncertainty, they don't just give you the best thing, they give you a distribution on everything. So what we're really after is we're trying to figure out what is the probability, the posterior probability of the various models. So I'll just call this the kth model, model K. Given all of your data. And what this really means in terms of which model you're searching for is which subsets of zeros are in and out of the model. So which betas are in and out of the model, which x's are in and out of the model. Different ways I can say the exact same thing. So model K is some model with a subset of beta j's. So j goes from 1 to p being 0. So we're not just going to work out the Bayes factor and all of this. This is a cursory step to getting everything right. And we're going to be computing different Bayes factors in a Gibbs sampling over and over again. And we're going to be cycling through and iterating through which beta j's are 0, which beta j's are not 0. And so we're going to be looking at that. How many possible models are there? So how many models do we need to look at? 2 to the p. Sometimes you'll see people put 2 to the p minus 1 right here. So in other classes, they might write that, or in various books, they might write that. Does anybody know what they're talking about? There's one model that they never want to entertain. Yeah, the one with 0 predictors in there. And so you might forbid one of these variables from being 0 in all of this. Very typically, people will leave the intercept in no matter what. And they won't rip it out and do model selection on there. And I usually advocate that. If you rip out the intercept and you're computing things like r squared, it might not have the interpretation that you're after. So keep in mind, if you remember this, r squared is this measure where we're comparing our model to the null model, which is the intercept only model, the constant model, where I just average all the y's, and that's what I use to explain all the variance in the y's. But I could use some x's and condition on those, and I could see how that reduces my explanation of the variance of the y's. And then you compare those in a ratio sense, and that's r squared. So that's supposed to just be a reminder from Stat 101. So very typically, we'll write in -1 that you might want the intercept model is required. But I think Anna's right. So in general, if you want to compare against everything out there, and even include the model where you explain nothing, you know, you can't even use the mean, then I guess you're right. But I think people like to restrict it to the -1 and make sure there's an intercept in their models. And I usually advocate that. No matter what, keep an intercept in there. Even if you feel like ripping it out, that it's really close to 0, I still usually say leave it in there. So in logistic regression, how many people are familiar with that? A lot of people. So it's like regression models where you explain where the response is 0 or 1s. So it's based off of a Bernoulli, non-IID Bernoullis. So they change, the p's change depending on the x's in there. The intercept is calibrating the base rate of 1s and 0s in the model. And so if you don't calibrate that and they're not balanced and equal, you will have made a terrible mistake. And so, and your models won't fit very well. So probably leave your intercepts in there. So this would probably be a column of 1s for the first thing. That's what I usually advocate. So this model sort of thing is kind of an abstract idea. Basically, there's a whole bunch of subsets of models where beta j is either 0 or something different. And so that's what we're figuring out. So what the Bayesians actually going to do, once they come up with this Bayes factor in a posterior probability corresponding to that model, they'll flip a coin and decide which model they want to go to in a Gibbs sort of fashion. So we'll look at that in a minute. And it'll iterate us through everything. So what we'll be doing is we'll be comparing lots of different models from each other. We might start with the full model. We might reduce it to this model. And then at the next step, if we did reduce everything and we think beta j was 0, then we'd be starting with this as our full model. And then we would have two possibilities. We'll either add in a new variable, and we'd have to calculate the Bayes factor for that, which is going to be very similar to the Bayes factor we'll write down today, or I'll remove a variable. So I'll do a coin flip and decide whether or not I want to include a model, a new variable into the model space, or reduce it again. And then I'll flip a coin and it gives sense. So I'll do some random sample. It's actually going to come from a Bernoulli distribution. So these are all just 1s and 0s if you think about, is the variable in or out? And then we'll do it over and over and over again. And when we iterate through all of our models, meaning that as we iterate in a Gibbs fashion, The models can reduce down to the null model or expand up to the full model, and keep doing that over and over again. And if you keep iterating through it, what you're getting is the posterior frequency of that model. So it's really giving you a proxy for this posterior probability of the model. So this is really a probability because this would be a discrete thing. It's countable things. Does that kind of make sense? So that's what we want to do. We just have to go through some math and get the Bayes factor for doing this. I'm going to show you just comparing the full model to this reduced model, but we could go the other way around. I could compute the Bayes factor from going from this model to that model. If I had the Bayes factor for going from this model to that model, how would I get the Bayes factor for going from this model to that model? Let me say it one more time. Say I was able to calculate the Bayes factor from going from this model to that model. How would I compute the Bayes factor from going from this model to that model? It's the inverse. Okay, you just invert it. So when you're expanding model space, you're just going to flip these Bayes factors over. So that's a pretty easy thing to do. So we have a big goal, is write a Gibbs sampler to iterate through this model space where we're removing betas from the model space or we're introducing new ones. Now what we could do is we could be even more ambitious. And instead of going from this model to that model, I could say, well, let me go from a model like this to models that reduce the variable space by 5 parameters simultaneously. 5 betas go to 0. You could do that. And you could work out that Bayes factor as well. And so the idea is that that might be a more ambitious move, and that might be akin to your step size in a Metropolis Hastings sampler, that you might be trying to make too big of a jump all at once. And so if you ended up having 4 of the parameters or something like that, saying that they're going to 0, but the 5th one maybe is strongly related to the y's, you would reject that whole block simultaneously if you tried to kick out one of the variables, and only 4 of them should be kicked out. And there's a 5th one in there that explains the y's. So it's common for people to just iterate this one by one. So, and remove one variable or add in one variable. So that's very typical. Let me think just a little bit more about this. These posterior probabilities that you get have a very nice property at the end of the day. How many people in here run stepwise selection with like adjusted R-squared or something like that? So R-squared is typically a very bad metric if you ran through stepwise selection. So stepwise selection uses a very similar principle to Gibbs sampling, but it's not giving you a full probability distribution. It is just trying to optimize and find the best model. So you pick some criteria, for instance, AIC or BIC, or something like the likelihood ratio altogether. It's just not fair to compare models to each other if one model has more parameters than the other model. So you want to penalize that somehow. We all agree with that. The Bayesian, when they use the point mass prior, they're penalizing it because they're having this penalty for your model complexity because it's coming in through the prior. So if you have a probability of a beta j being 0, and you've got like 9 of the variables being 0, you're going to have that probability powered up to a 9 ultimately in your posterior. So that is doing automatic regularization, or that penalty. So regularization means penalty. What's really nice about this is a posterior probability, what the Bayesian's giving you. In stepwise selection, you pick some criterion, you might come up with an adjustment to R-squared. If you use R-squared, you're going to overfit everything. So because it doesn't have any penalty on the model space. And so just, if you're trying to think about fit or something like that, and you had a scatter point of, if you had a scatter of data points right here, and I picked 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points in this. You might think that actually looks terrible. I'm going to put another data point over here and one here because somebody's going to say that the variance is increasing. Get rid of that one. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 data points. One good model that explains the trend in this data might look like that. So, and I might be able to come up with some credible bounds or confidence bounds on this regression line. They would look something like this. So that, in a Bayesian sense, if I were trying to think about the betas are random, so it can kind of roll this line around, and where does it roll most? Near the endpoints. And so usually the posterior bound for something like that would look like that. And that might be a very good explanatory model. So this might be a linear model right here. So that's a 1-degree polynomial. But I could come up with a higher degree polynomial that looks something like this. Okay, that might not look like a function. I maybe should have gone through that point first. Okay, that looks more like a function. But you get my point. That twisted a lot for that one data point. And if I would have moved it a little bit, it would have changed the line considerably. These are supposed to be going straight through these points. So this would be an interpolation scheme. And if I took, how many points do I have right here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. If I took a 13-degree polynomial, I could fit that thing perfectly. Why don't we like models like that? Because they don't predict very well. So if I ended up seeing another data point right here, I might explain it by this thing right over here. And the variance on that line is going to be nil. So if you interpolate it, it's going through with absolute certainty. There's no error in any of it. And so this line would be closer to that data point. So that would be a little bit better thing to do. And so you always want this sort of regularization of the model space. So you can use any criterion you want. There's R squared adjusted that has a penalty that's attached to R squared so that you don't do this. You could use AIC or BIC. They both have penalties in terms of the parameter space. So AIC penalizes it by 2 times that thing, and BIC penalizes it by log n. And so they're close to each other. They're a little bit different, and the goals are a little bit different, but they're similar. Nobody's ever told us which one we should actually use, and that's because there's no answer to any of this. So what's your favorite criterion that you learned like in undergrad? I like this Mallow CP thing for a little while. I was like, that one's pretty cool. So it's a little bit fancier. It has a penalization term. And so does anybody know what it means or what the interpretation is? Probably not. So anyway, weird things can happen with stepwise selection. So you could get a model. You could say your best model. So let's say stepwise selection. With, I'll say, adjusted R squared. This isn't my favorite thing in the world to do. We teach it to undergrads because it's easy to explain, I think. But it's it at least has like the right ideas baked into it. So adjusted R squared, your best model might look like this. Best model might say out of p variables, it might say beta 1, beta 5, and beta 6 are not equal to 0. And everything else is equal to 0. And then your second best model might be something like this. Beta 3, beta 9, and beta 12. I'll put beta 1 in there because it's the intercept, so maybe you've been at least smart and you've constrained everything. So maybe your second best model is that one that explains the data the best. If you got this back in your algorithm, what would you think? That sucks. So, because they're not nested in each other. And so the second best model should probably contain the best model in there. And with stepwise selection, with these different penalization factors that you can use, you can get this sort of behavior. I've been a bit dramatic in, saying that that's what you could get, and I can engineer examples that do that. Usually with real data, it's not that bad, but this can happen. You can also do stepwise selection with p-values as well, and people sometimes do that, the p-value for a beta j being 0. It doesn't have any penalization built into it, and these sort of things can happen. So with this that we're computing, that never happens. So your second best model will be nested inside your best model. And that's because what the Bayesian is giving you is a posterior probability on things. And probabilities are additive. So if you ended up doing this maybe with p-values instead of adjusted r squared, that same p-value problem of the non-additivity of the p-value will plague you if you do this. So let's get rid of adjusted r squared and beat up on p-values one more time. So do it with p-values or something like that. Or you just have a p-value for that corresponding hypothesis. And you can get results like this. And I don't like that because I think that the second best model and the first best model should have something in common with each other. So that's one thing that this procedure will give you. It's more computational than the other procedures. They're giving you a full distribution of everything, but I find this to be desirable. And if I find lots of good models with high probability, I usually report up and tell you what the addition or subtraction of one variable will do to everything until there's a big break in the model space, and then I think, oh, wow. You know, these 4 models seem to explain everything and they're nested within each other. So I think a scientist could look at that. Where if I did something like this with stepwise selection, and I came back with 4 best models and they have nothing to do with each other except for the intercept, I would imagine they would be confused. So I wouldn't even know how to explain that. Okay. So we know the goal. Let's figure out this Bayes factor. Again, H naught, just beta j is equal to 0 versus H1, beta j is not equal to 0. And we're going to compute the Bayes factor. I always put the null model on top in my Bayes factor. Be aware, not everybody in the world does that. And so I've had an hour-long conversation with somebody, and the mistake was we didn't have a chalkboard around us. And we were trying to, and it's like, no, I know this Bayes factor by heart. So, and all of a sudden it occurred to us after about an hour, we were explaining the math wrong to each other because we were on inverted scales. So just be aware that can happen. So this Bayes factor, oh, let me tell you what the prior is again. So prior for beta j is going to be pi naught. So that's my posterior probability of the null. Beta j is equal to 0 before I see the data. So times this delta function plus 1 minus pi naught times our alternative prior. So I'll write that down as a normal, centered at 0 because that's what we're testing, and it's going to have some variance. And as we know by now, that makes a big difference. So that's how we're comparing zeros to each other, zeros to something that's other than 0. How far from 0 do we need to be before we're willing to reject it? If we remember the Barron's, or the Lindley-Bartlett paradox, too many names, that is psi squared goes out to infinity, you'll put all your weight on the null model, and you'll kick that variable out, the probability one. So you don't want to make it flat. How do you really think about that? What I usually do, my cheapest answer I can give to you is standardize all of your data, and then maybe pick that to be 1 or 2, something like that. So 1.96. So 1.96 squared or something like that. So I need to be 2 standard errors out. You might think that that sounds a lot like the p-value game that we're normally playing, but keep in mind we're getting the additivity feature of the posterior probability on model space. So it's different. It's regularized differently. So our Bayes factor is going to look like this. So I'll have my likelihood, my betas, given x and y, times my, in some sense, I say it this way, When I write it down this way, I mean this is an infinite point mass. And kind of when I'm writing it over here, I just mean it's a 1 or a 0. And we talked about that a little bit before in one of the review sessions. I don't really care how you think about it, just as long as you compute the integral correctly. So this is going to be my prior on my null. And I'm going to say every other variable is in the model because I'm only testing as one of the variables 0, 0. So this is going to be my prior on beta minus j. What does that look like? What do I mean when I'm expressing that? Yeah, but what is this whole distribution?
The joint distribution.
Exactly. It's the joint coming from all of these. So I'm putting this normal prior on all of those. So this is just going to be our product. I goes from 1 to j minus 1 times my normal prior on everything. So 1 over 2 pi psi e to the minus 1/2 beta I squared over psi squared. And then I'm going to have a product. I goes from j plus 1 p 1 over 2 pi square root psi e to the minus 1/2 beta, I'll call this I prime, squared over psi squared. So it's that joint normal, and you could write this down multi-dimensionally, and you'd probably do that. So that's what that prior is. It's the prior on all the other stuff. And then I'm going to integrate over d beta 1 all the way to d beta p. And we'll need to work through this integration a little bit. And then I'm going to integrate something similar in the denominator. This is going to be pi on beta j. This is all in my alternative. So this is going to be a multivariate normal on all of the beta j's. So, sorry, no j in there. So just all of my betas right here. So you could write this down like this. E to the minus, I'll do the same notation I did before. I goes from 1 to p, 1 over root 2 pi psi, e to the minus 1/2 beta I squared over psi squared. So keep in mind when we do this, I've got an extra psi down here than I do up here. So if you look at this, I've got this psi in the denominator. This is being powered up p minus 1 times. This one is being powered up p times. So this thing for the jth one doesn't have a normal distribution attached to it. It has that point mass. So p beta. In this beta, I just mean this to be the overall beta right here. So this is the same thing down here. Where am I integrating over? Negative infinity to infinity on everything. And I'm never inclined to write down p integral signs over here. So we need to calculate this Bayes factor. I don't want to do everything for you, simply because that's problem 1 on the homework, but I'll do enough so that you can fill in the blanks. So let's look at the numerator. The numerator is the harder one than the denominator because it's got that little point mass in there. So let's just write this down. Let me write down the Bayes factor first, and then I'll write down the calculation for the numerator that you'll need to use on your homework. So let me just write down the Bayes factor so that at least we've got it. And I'll write it down a little bit superfluously so you can see where everything is coming from. So let me give you some notation first. notation. I'm going to call E for expectation. Actually, let's do V first. The variance is going to be 1 over sigma squared X transpose X. So this is my cap X. Plus 1 over psi squared inverted. The expectation is going to be V, this same thing right here, times 1 over sigma squared. A lot of people forget about this sigma squared right here. I've done it in the past. So X transpose Y. So just to be clear, we've seen something just like this before. Very similar. If I didn't have that part, oh, this should be the identity. So that's the identity matrix right here. So this has the same dimensions as X transpose X. What's the dimensionality of X transpose X? P by 1. So this a P by, or this a P by P, that's a P by P. This whole thing is just a P by 1. So that's the dimension of beta right here. So we've seen this formula very similarly. If we got rid of that part, that would be very similar to using a flat prior on everything. And if we were doing just inference on beta, that's fine. But if we're doing a model selection, i.e. a model comparison, you can't use the flat prior. And so you need to calibrate it somehow. But if we didn't have that, this thing would be our estimate for the regression line. These sigmas would cancel each other out and everything. So that sigma is getting flipped upside down in the variance calculation. Has anybody seen this solution before? Does that look familiar to you? It's ridge. Yeah, exactly. So this is the ridge regression solution. So this isn't talking about model selection per se. It is regularizing the model, but it's not forcing anything to be zeros when you do this. And so this is the ridge regression solution. Let me give you some similar notation. I'm going to call B0J. This should look almost entirely the same. This is going to be 1 over sigma squared X minus J transpose X minus J plus 1 over psi squared I. This I right here is P minus 1 by P minus 1. This one right here was P by P. So slightly different I's right there. And the expectation corresponding to this will be this thing. V0J times X transpose minus J. I've done it again, I forgot my sigma squared. There's a 1 over sigma squared in there. X minus J times Y. So Y isn't reduced in any way. You've always got all the same Y's in there.
Shouldn't it be inverted in the variance?
Yes. They're meant to look the same. Yeah, that's right. So this is kind of like a ridge solution for the reduced model. So that's kind of interesting. If you don't know what ridge is, I'll guarantee to have explained it to you by Friday. I'll probably get to it in the next lecture. Quick question, who created ridge? lots of people. So I say Tigranov, some people say other people. So statisticians usually pick other people to assign this to. I learned about it first in computer science when I was taking optimization courses. So I thought, oh, that's cool. And it actually did come about through mathematics. Somebody that was doing kind of computer science-y stuff before it showed up in statistics land. But not too soon after, statisticians were super aware of this. So it probably happened around the 70s that everybody was colliding in on this. That kind of surprises me. I would expect this to be a result that they would have used in the 1700s. So, but it took a lot longer for people to, I guess, get there with this. Okay, here's the base factor. It's going to look like V0J. This is determinant 1/2 divided by, I'll put it here, psi p minus 1 e to the plus, I'll circle that so we remember it, 1/2 expectation 0j transpose v 0j inverse expectation e0j. And this is going to be this. Same stuff, but just with the other v's and e's in the denominator. V to the 1/2 divided by psi to the p, e to the plus 1/2 e transpose v inverse e. And you've got all the notation for that. So I left these psi's in there, just like that, although all of them but one of them cancels, just so you could see where they're coming from. So, does anybody know where all these terms come from when we solve the integral? So we get this plus right here, that's a hint. It's the completion of the square thing. All of those integrals, you just need to complete the square. So let's do one of them. I'll take you through some of the steps. So the numerator. It's going to look like this. Integral e to the minus 1/2. I've gotten rid of the, I probably shouldn't have. Let me keep that in there. 1 over root 2 pi square root let me not do that. Too many choices. E to the minus 1/2 y minus x beta transpose y minus x beta, this is the cap x, cap y, divided by sigma squared. I'm going to get rid of my normalizing constant right here. So this part, the 1 over square root 2 pi term, I'm just going to cancel it out because in my Bayes factor, it appears in both the numerator and the denominator. And they cancel each other out exactly the same. So this is my likelihood. So if you go to work this out and you put in all your normalizing constants on your likelihood in your denominator and you don't do it in your numerator, you're about to make a mistake. So you need to encode the likelihood exactly the same in both the numerator and the denominator. So I'm going to get rid of that normalizing constant. So times beta j is equal to 0, that delta function. And then I'm going to have this term. 1 over root 2 pi square root psi. This is going to be p minus 1. And this is going to be multiplied by, I'm going to give myself just a little bit more room here, e to the minus 1/2 beta minus j transpose beta minus j. And this is going to be divided by psi squared. So that's right here. d beta. So that's the whole integral that we need to solve. That's the exact same thing that we wrote down last time. I just wrote it out in matrix notation. So this is the key step, I think, that you need. So I can rewrite this up to proportionality. This is going to be integral 1 over root 2 pi square root psi raised to the p minus 1. That's still just that stuff. I just pulled it out. And I'm going to write this down just a little bit differently. E to the minus 1/2 beta minus j transpose. There's an open brace. This is going to be x transpose minus j. It makes it hard when I make mistakes. So on my notes, I know this is an error. I know what it is. X, there we go. I over sigma squared x minus j plus I over psi squared. Beta minus j. And then I'm going to have one other term. Minus 2 times this thing. So this is my minus 2 linear term. I'll just remind us, this is our quadratic term. And my minus 2 linear term is going to be minus 2 beta minus j transpose. That's a vector. 1 over sigma squared x transpose minus j y. D beta. Right there. So what I've done, apologies for throwing it right in the corner. So I'll not erase that so you can come over and have a look at it at the end of class. So what I've done is I've just written this out in terms of the quadratic term and in terms of the minus 2 linear term. So what I've done in here is I've used that relationship that I wrote down over here where I've got my beta j is equal to a 0. And I might as well just make that beta j a 0 in here and make it at 0 everywhere that we see everything. So what I've done is instead of making the beta j explicitly just 0, I've also ripped that row or that column out of the X matrix. And that's what's going on right here. And so I've rewritten my likelihood term using this by imposing that I know the beta 0. Even though it doesn't show up right here as 0, it's going to be 0 when I compute the integral. And I integrate through everything. And so another way you can think about that is just writing everything with the reduced form of the x's. And so this is what that integral reduces to. It's proportional to, because I only wrote down the quadratic term and the minus 2 linear term, which are the only things you need to know to solve that problem. So when you complete the square and you get everything, you get this. Right there. So keep in mind this variance is on top, right? And everything is flipped over here. So that's because everything is getting flipped over in the completion of the square. And that thing is getting flipped over in the completion of the square. So this is the completion of the square term. So we've seen this before. This looks like the expectation squared divided by the variance. But we don't say that when we're dealing with matrices and vectors. So that is that equivalent form in matrix notation. So hopefully you can just explain that to yourself and go through those details and write out this Bayes factor. So that's the name of the game. This is very similar. This is just the completion of the square term, and I don't have to deal with anything where the beta j is 0. Does that make sense? Cool. So all that stuff that we've learned over and over again keeps coming up. And that's a thing. In all of Bayesian world, all the same stuff comes up over and over and over again. You just layer it in there. So there's that Bayes factor. So here's what we're going to do. I'm just going to give you the semblance of the idea of SSVS. So what we're going to do, oh, and also the corresponding posterior probability for this. The probability that beta j is equal to 0 given everything else, the x's and the y's and everything else. And what I'm doing here, is what we're doing in our algorithm is we're integrating out all of the betas. So we're not carrying them with you. In some models, you need to carry the betas with you. Here we can analytically integrate all of them out. And so we do that. So this posterior probability that beta j is equal to 0, i.e. the null hypothesis, we've computed the corresponding Bayes factor for it. And so all we do is we take 1 plus 1 minus pi naught over pi naught times this Bayes factor, inverse, invert all of that. So I can change this Bayes factor into a posterior probability. So here's what we're going to do. We're going to start with the full model. And then I'm going to just iterate through this for loop. For I goes, I'll say t goes from 1 to cap t. So large number of iterations. So big. How big should it be? Until it converges. So if I were monitoring convergence, I'd probably monitor the posterior frequency of beta j's being 0. So I just look at that frequency and make sure all of them stabilize. So you need to monitor something in a Gibbs sampler. You could monitor that. I also will usually monitor the likelihood as well. I'll take my answer, plug it back into the likelihood, and I'll look at how the likelihood is converging. So I probably monitor several things. In Spirit, that's what you can do. Theoretically, you should check everything, every little possible thing that could change. So that means every transformation of everything should converge as well. Most people aren't that ambitious. They'll just monitor the posterior frequencies. So what we're going to do is we're going to iterate through a loop in here. So I'll say t goes from 1 to cap t. And what we're going to do is we're going to entertain different scenarios. So in this first scenario, I can either try to include a new model into everything, or I could subtract a model out, or a parameter out of the model. So because there's only one possibility for that, usually what I would do is I would just flip the coin, and if I said I want to include the model, a new parameter into the model, and if there is no parameter to include into the model because I'm already at the full model, then I just say, well, that happens with probability 0, and I skip the step. So what you're going to do, so with probability 1/2, we're going to remove beta p. And so with probability 1/2, I might include beta p. And so if I already had beta p in the model right here, I wouldn't do anything. I could make this more efficient and only cycle through variables that make sense, but I would need more conditional statements. If you can't include the model, the parameter into the model because there's no more, you don't do anything. So if you've already included beta p into all of that, then I wouldn't do anything. So, but what I would do is I would compute the Bayes factor, and then I would compute the probability of removal. And I would compute down here the probability of the inclusion. What's kind of nice about this is you're including this metropolis sort of step in there, and it's symmetric if you pick it to be a half, so everything cancels out. So this is really metropolis within Gibbs. But what am I going to compute this probability right here? So if I were dealing with the full model, and I flipped the coin, and I flipped it and it said it's going to remove a probability, one of the beta p's, I compute that Bayes factor that we just wrote down, compute its probability, flip that coin, and if it lands heads, I remove the parameter, the coefficient from the regression model. If instead I flipped the coin and it said to include something, but it was already included, I just skip over that step. I've already included it, it's in the model. The posterior probability of inclusion would be 1 for that. Just so you know, if you actually did compute it, because you would be computing a Bayes factor that is the same in the numerator and the denominator. And so you're just going to iterate over this idea over and over again. So you're going to start with some model, you're going to either remove something or add it. You're just going to keep doing that over and over again. So what's changing in the Bayes factor when you do this? The Bayes factor is either getting flipped upside down or staying in this way. So if I'm removing a variable, Bayes factor looks like this. If I'm including a variable, I'm flipping it upside down, this Bayes factor, and computing that posterior probability. What's changing in the Bayes factor? Only the x's are changing. So keep in mind, this right here has something to do with x minus j. And this has something to do with x right here. And so what I'm going to be doing is when I'm going to remove a variable is I'm going to compare it to my x's that are currently in the model space, and I'm going to be removing a column from that. And if I include that variable, I just flip this thing upside down. And so all that's changing in this for loop is your x's and whether or not you're inverting this ratio. Does that kind of make sense? So I'm leaving you the details. Now, I'll make you a deal. If you absolutely try to do this and you can't get it up and running at all, and you're nervous because your previous Gibbs samplers didn't work all that well, you can use built-in software to do that. So R has a plethora of packages on this, MATLAB has stuff. I'll let you find it, but I at least want you to attempt coding this thing up. It's not that hard to do. So we'll come back next time, talk about a few more details with this, and then we'll talk about ridge and lasso a little bit. So if you want to skip ahead, there's probably some lectures on my web page from previous years if you want to skip ahead and look at all that stuff, but I'll give you an introduction to those. And I'll try to run a lasso packet for you so that you can see what the lasso actually does. Thanks, you guys.